Okay. Um, well, Friday's a test, so yeah, feel the excitement. Um, so yeah, today's just about stuff related to the test, which is so I have a request to look at a homework problem, which I'm sure you guys would appreciate too, and that can also to some extent be helpful for test. And then anytime not spent on homework problems, I started reviewing last time. We'll look at the practice test. How many of you have actually worked through a practice test? Okay, that's enough to go on. But not surprised that it was far from unanimous. So actually, okay, I'll just send a reminder. Um, it's on the course website on the lectures page, but I'll just send a direct link to all of you a little later today, just for everyone's convenience. So there's a practice test and the solution, so be sure to look at the solution as well. Okay. Now, all right, so a problem I'm going to look at, and actually you're not the first to ask me about it. This is 13.8, number 8. So the version of a problem that I'm seeing here is the absolute max and min of this function, x squared plus y squared plus or minus 4y plus 4, where x and y are limited to this domain labeled R, instead of all points in R2, that x squared plus y squared is less or equal to 9. So we're looking at a disk centered at the origin and of radius 3. So this whole region here is your R. So what you have to do is find critical points, and only the ones that are within R, so in the interior or on the boundary. So that's where you could have a local max or min. And then the second thing is to check the boundary. So only from both points, boundary points and any critical points in the interior, are points where there could be an absolute maximum or minimum. Now, since we have a circular domain here, it's actually possible to do a problem in 2 different ways. So you can stick with Cartesian coordinates x, y, or you can use polar coordinates r and theta. So I can go ahead and show you polar coordinates, because polar coordinates we're going to be dealing with a lot during the remainder of the semester anyway. So you saw these in Cal 3, and in case you've forgotten, if x is r cosine theta, y is r sine theta, so that's how, because r is your distance from the origin, and theta is the angle that the point makes of a positive x-axis. So if you're given r and theta, here's how you get x and y. And to go the other way, you have r squared equals x squared plus y squared. So r is just distance from the origin. And then, as for theta, tangent of theta is equal to y over x. And that does not mean necessarily that theta is equal to arctangent of y over x. There's a reason why I didn't write it that way. It depends on whether x is positive or negative, or also there's a separate case if x is 0. So what you can do is you can express this function in polar coordinates, and then a domain in polar coordinates, which will have a simpler description. And then work out the problem in the exact same way. You're just dealing with different variables. You're just taking partial derivatives with respect to r and theta instead of x and y. So in that case, if I define function g of r theta to be the original function f of xy, but x is now r cosine theta, r sine theta, this particular function translates pretty nicely to polar coordinates because you have x squared plus y squared already there. So that's just r squared. And then the minus 4y becomes minus 4r sine theta. And then you have the plus 4, because 4 is 4 in any coordinate system. And now to find critical points, you have, you're taking partial derivative with respect to r and theta. So dg dr. So r and theta are now playing a role of your x and y. So if you're differentiating this with respect to r, what would that be?
2r minus 4 sine. Oh no,
2r minus 4 what?
cosine.
No.
No, that's in respect to theta, so it'd be sine theta.
Yes. Yeah, so only differentiating with respect to r at this point. Okay. And we want this to be 0. Now here, this equation involves both r and theta. So it's not really prudent to try to solve this equation for r and theta just yet. We need to look at the other one. Partial with respect to theta. So what is the derivative of this with respect to theta?
R squared. Let's see. Be negative
Negative
4
4 cosine theta.
cosine theta.
Yeah, minus 4r cosine theta. Now, our domain is, okay, so r still points r and theta, but r is between 0 and 3, and theta is between 0 and 2 pi. So we have those limitations to keep in mind. Now, it would certainly be easy. So if we look at, for instance, dg d theta, when that is equal to 0. So what would make that, just a second partial derivative, dg d theta, what would make that equal to 0?
If r was 0.
Yeah, so r equals 0. Or, what's the other possibility?
Theta equals 90.
Yes.
Or pi over 2.
Yeah, pi over 2. There's one more.
Oh, it's 3 pi over 2.
Yeah, so at the top of a circle, pi over 2, and at the bottom of the circle, cosine is the x-coordinate. So if any one of these happens, then yes, you have dg d theta, at least, is 0. But we need both partial derivatives. Okay, you need both first partial derivatives to be equal to 0. So now we need to look at dg dr. So we can plug all these possibilities into dg dr and see what happens. All right, so r is 2r minus 4 sine theta. Okay, so if r equals 0, we just go ahead and plug it in. We get minus 4 sine theta is 0. Then again, actually, this isn't even necessary. Because if r equals 0, where are we in the plane? Like, what's the x and y? It's 0, 0. So now, theta can be 0, pi, any multiple of pi, but you're still at the same point. So at the origin. So 0 anything is a critical point. And then you look at the other possibilities. Theta equal pi over 2. Well, sine of pi over 2 is 1. So 2r minus 4 is 0. So we get r equal 2. And then theta equals minus, or 3 pi over 2. What's sine of 3 pi over 2? At the bottom of a circle. Yes, I heard someone whisper that. Negative 1. 2r plus 4 is equal to 0. So r is equal to minus 2. Okay. So now we have, so this gives us a critical point. R is 2, theta is pi over 2. And this gives us a critical point. R is minus 2, 3 pi over 2. But we'd like to see, again, where does that put us within this disk? So we have the origin, and then the point, r equals 2, so 2 away from the origin at the angle pi over 2, puts us right here. So this is xy is equal to x is 0, y is 2. And then r theta is equal to r is 2 and theta is pi over 2. Now, so that's this point. And then here we have the origin. What about this point? Where does this put us? When you have a negative r, what does that mean? It's kind of strange. How do you handle that? Because the angle, if everything gets the angle, 3 pi over 2, that's down here. And normally r refers to distance from the origin, but what do you do when a distance is negative?
Go backward.
Yeah.
It's the same point.
Yes, it's just the same point again. So this is also minus 2, 3 pi over 2. So we really only have 2 distinct critical points. So these are candidates. And so what we could do is plug those back into a function, either in polar coordinates in this version, or in terms of xy in the original version. So my list of candidates, I'm going to stick with xy. I have 0, 0, and 0, 2. So I can plug those into the function, and I get 4 for this point, and I have, okay, so 4 plus 4 is 8, minus 4 is 0 at that point. Okay, so any questions about critical points? And you've been doing this in xy, but the procedure is exactly the same. You find both partial derivatives, you see wherever equals 0. Now, the only other thing left to do is to check the boundary. Fortunately, this is one reason for switching to polar coordinates, maybe the main reason, is that the boundary is so much easier to describe. The boundary is x squared plus y squared is equal to 9, so the circle that encloses the disk. But in terms of polar coordinates, how can we express that easily in terms of polar coordinates? R equals 3. So now all we have to do is set r equal to 3 in a function. So g of 3 theta is equal to, okay, so 9 minus 12 sine theta plus 4. So we get 13 minus 12 sine theta. So now we're, and theta is between 0 and 2 pi. Now we're solving a one-dimensional minimization problem, or finding a max min problem. So if I call this h of theta, just for convenience, take the derivative of that, set it equals 0, and you get minus 12 cosine theta, and we know where cosine theta is equal to 0. So theta is equal to either pi over 2 or 3 pi over 2. So those are the only candidates for a max or min along the boundary. So now what we can do is, so which points are those? These are on the circle here and here. So our candidates are x is 0, y is 3, and x is 0, y is minus 3. So in this case, our function reduces to 13 minus 4y. So we could go ahead and plug those into the function, and we get 25 in this case, and 1 in that case. So now we can see from there which is the max, which is the min. We just take the largest and smallest. So this is the absolute max, and this is the absolute min. And you're done. So the alternative approach would have been to take the derivatives of this with respect to x and y and set those equal to 0. And what would have happened is you get like the derivative of the original function with respect to x is just 2x, so x is 0. So any critical points have to satisfy that. And your with respect to y, you have 2y minus 4, which gives you y equals 2. So it picked out this critical point, and then you set x squared plus y squared equal to 9 up here. So at least in this case, the boundary condition is still not difficult to enforce. And you get, like I said, I wrote over here, 13 minus 4y, which, as a linear function, it has no max and min. So you can only check the boundary points. So in this case, for boundary, x squared plus y squared equals 9. So f of xy reduces to 13 minus 4y, and you only consider y values that can actually be on a circle of radius 3. So minus 3 to 3. And you can plug in those boundary. 13 minus 4y is not going to have any critical points. Its derivative will never be 0. So you plug in the boundary y values and get your candidates that way.
How do you get f of x and y equals 13 minus 4y?
Well, this becomes 9. Yes, so the restriction of f to the boundary is equal to that.
I don't understand.
Well, on the boundary, x squared plus y squared equals 9.
But what numbers are you plugging into x and y? 3?
No, I'm just saying
So r squared equals
this,
x squared
this,
plus
yeah,
y
x squared
squared.
plus y
Okay,
squared
yeah.
as a whole
Mm-hmm.
is 9.
Okay, yeah. I see.
Yeah, okay. All right. So any questions about this kind of max-min problem? Okay. Does anyone want to ask about any specific practice test problem? Those of you who haven't looked at it. Alright, directional derivative. Okay, so your function is 2 square root of x minus y squared. And that's for oh, yeah, okay. I can see why this one might, the way it's described, pose a confusion. That's why I made sure when I looked at the real test to not have similar confusion ensue. Okay, so what the wording is so find directional derivative at the point 1, 5 in the direction toward the point 4, 1. Okay. Now, so if you okay, so 1. Okay. Yes. Okay. Okay, so the idea is, in what direction, at what rate is the function changing if you're at this point and you're traveling towards this point? And that's what I meant in the direction toward the point 4, 1. It's really this vector that, that you want. So u is going to be the vector obtained by subtracting this from this. 4 minus 1, so subtracting the x-coordinates, and then 1 minus 5, subtracting the y-coordinates, which, and over its magnitude, because it has to be a unit vector. Okay. Alright, so, alright, so, imagine this was a, okay. So to work out the magnitude of that, it's going to be 3 squared plus minus 4 squared, square root. That's, so we get the square root of 25 down below. So we get 1/5. So that is your u.
I don't get that 3 squared plus
Oh, that's how you take the magnitude of this vector. You take square root of the sum of squares, distance formula. Yeah, okay. All right. All right. So what I make sure of on a real test is that it's completely unambiguous as to what direction I really want for the u. And again, you just have to remember to make sure that it's a unit vector. Okay. So now that we have our u, well, the directional derivative is a gradient of f dot product with u. So we have u, we just need the gradient. So the gradient, that's vector consisting of partial with respect to x, partial with respect to y. What are those?
1 over the square root of x.
Yeah, because you have 2x to the 1/2, so you have 2x to the 2 times 1/2 x to the minus 1/2, and that's all for df dx, and then for df dy,
Negative 2y.
minus 2y. So 1 over square root of x and 2y, and you plug in the pointer you're given, 1, 5 in this case, so we get 1 and 10. Oh, forgot to minus. Here, here. Okay, thank you. All right, so now we know what to take the dot product of. 1 minus 10, dot product with 1/5, 3 times minus 4. Any scaling constants like this, and I tend to leave them factored out like this just to reduce clutter. You can always move that out here. Dot product with 3 minus 4. So you got to know what dot product is, multiply corresponding components, and add them all up. The things I saw last time we gave this test 2 years ago were kind of scary, like basically not remembering what dot product was. You got to have it burned to your brain. You're going to need it all semester long. So when you carry that operation out, what are you going to get?
43 over 5.
So you're going to get 1 times 3 plus minus 10 times minus 4. And so you work all that out, yes, you get 43 over 5. So your final answer for this, directional derivative at a point, is just going to be a number. So get your u from a description of a problem, make sure it's a unit vector, so divide by its magnitude, and take your gradient, whatever point you're given, plug that in, then take the dot product, done, 16 points. But this should be among the shorter 16 points as far as problems in this test go. But any questions about it?
So that's one of the easiest of the 16 points?
Well, I guess it depends on what you remember. But yeah, in terms of some mechanics, they're just less involved. Because like if you compare like the next problem, finding max min, you got to find the critical points. Then however many you find, you got to classify them. Are they max, min, saddle point? There's just more to do. Okay. I mean, we could use whatever time we have left to focus on as many of these as we can, but I'd like to prioritize. So, are any other ones that one in particular would like to look at? Otherwise, I'll just pick one.
Want to do number 6?
Yeah, that's actually what I would have picked. Since I was just talking about that being a longer one. Okay, so number 6. So this is in contrast to the one I was doing earlier today, because there's 2 kinds of max-min problems. You're finding local max and min, that's what you'll see in a test, and then there's absolute max-min where you have to take a boundary into account. That will not be in a test, although I could put it on the final. Final is comprehensive. Department, maybe do it. Okay. So fxy is 3xy minus x squared y minus xy squared. Okay. Okay. Algebraically, this is going to be a good one to look at because it shows what sort of things can come up. So if I actually find local max, min, saddle points. Okay. Because actually, from this example, you're going to get multiple critical points, which is good for practice. But you just never know. Sometimes you get only one critical point, and that can happen. It just depends on the function. So we need partial with respect to x and partial with respect to y, both 0. So what is the partial with respect to x?
3y minus 2xy minus y squared.
Okay. And for y?
3x minus x squared minus 2xy.
Minus 2xy. Okay. Now, and actually, if I were to predict where there's the greatest likelihood of having a stumbling block is right here. Why? Because it's everyone's kryptonite, algebra. So, first, see what you can factor out. Here, like you can factor out a y. And we have 3 minus 2x minus y. And here you can factor out an x. So we have 3 minus x minus 2y. So what's happening is you have to consider different cases. So if we start with, say, partial with respect to x being 0, this means that either y equals 0 or 3 minus 2x minus y is 0. So what you can do, and then down here we have x equals 0, or 3 minus x minus 2y equals 0. Okay, now let's first consider the case y equals 0. So that immediately makes partial of f respect to x equal to 0. Now I need to move to partial respect to y. So go ahead down here, fill in y equals 0. So we have x times 3 minus x. And that must be equal to 0. So what do we get as critical points from this case? So y equals 0, we assume that at the outset, and what else do we get?
X equals 0.
Yeah, so x being 0 makes it 0, and
3.
yeah, so we get 2 critical points from this situation. All right. Now, if this is not true now, that's case 2, the only possibility left is we must have the other factor in this must be 0. So in fact, I can say that, I'll just rearrange this, y is equal to 3 minus 2x. So now what you can do is substitute that into df dy. So fy is equal to x times 3 minus x minus 2, 3 minus 2x. So you go ahead and simplify that. So you get 3x minus 3. And that must be equal to 0. So what does this tell us in terms of finding either x or y for a critical point? What are the possibilities? Yeah, so we get x equals 0 or x equals 1. We have to check both. So now what you can do is, now we have values for x, you can plug that back in here, because y has to be this in order for fx to be 0. So we go ahead and plug it in, and in this case we get 3, and in the other, y is equal to 1. So we get 2 more critical points, 0, 3, and 1, 1. We've exhausted all the possibilities now, because these two things are the only way to make fx equal to 0. We can't go back and try anything else. And so we followed those paths to their ends, bless you, and now we have 4 critical points altogether. All right. No, the real test problem's not going to be this long. Right, this is often what I do. Is that sometimes I will make the practice problem more challenging than the corresponding real problem, because it's more illustrative of the concepts and so forth, because time's not an issue yet. Okay. I tried to be sympathetic to your need for speed. Okay. Now, what's left is to classify each of these critical points as local max, local man, saddle point, or inconclusive. And for that, we need the second partial derivatives. Okay. And these are arranged, you don't have to write it this way, just the Hessian is a collection of all the second partial derivatives. Okay, so now I'll repeat the first partial derivatives because we need those. Okay, so it's easier to leave them in this form because who wants to do a product rule Miller's test? Okay, 3x minus x squared minus 2xy. Okay, so we go ahead and compute the second partial derivatives. So what is fxx?
Negative 2x.
No.
I mean negative 2.
Yeah, 2y. And actually, similarly, fyy would be,
Negative 2x.
yeah. Okay, now, but now we differentiate this with respect to y. What are we going to get?
3 minus 2x minus 2y.
2x minus 2y. And then this will actually be the same. 3 minus 2x minus 2y. Now, before you go any further, it would be a good idea to, because you have to take determinant of this, but you might as well wait until you've plugged in all the numbers. So we have 4 critical points. So we have 0, 0, 3, 0, 0, 3, and then 1, 1. So we plug in 0, 0 into that. Well, we get not much. We get 0, 0, 3, and 3. We plug in x is 3 and y is 0. So you're going to get 0 minus 6, and then 3 minus 2. So minus 3, then minus 3. Okay. And then for 0, 3, okay, so you get 0 down here, minus 6, and then you're going to have, okay, x is 0, so you have minus 3, minus 3. And finally, when you plug in 1, 1, so you get minus 2, and then you have, okay, so minus 1 and minus 1. Okay, so what you do is you compute, so for second derivative tests, you compute this quantity d for determinant fxx, fyy, minus fxy squared. So multiply the ones in the diagonal, subtract from that the product of the other two elements. So this is a 2 by 2 determinant, which comes up in so many other classes anyway. Or you can just remember this. So what we get in case of 0, 0, we get minus 9. For the second case, we get, for 3, 0, we get plus 9. For 0, 3, we get, okay, so for 0, 3, we get 0, oh, wait. Sorry, that's minus 9 for this one, minus 9 for this. So they're all three, first three are all minus 9. The last one is 4, is 3. Okay. So that's what we get for the value of d for all of these. When d is negative, what's the conclusion? It's a saddle point. So this graph has 3 saddle points. Okay. Oh. Okay, right. When it's positive, that means it's a local max or a local min. Which is it?
Max.
It's a max because these diagonal entries, you really only need to look at one of them. In this case, you're going to have the same sign. They're negative. So because fxx, fyy are negative, this is a local max. And that's it. So all the critical points are classified. Max, min, or saddle point.
This is a local max.
All right. Questions? We still have some time. Of the remaining 4 problems, is there one particular you'd like to look at? Or I'll just pick one. All right, I'll pick the chain rule, number 4. So you're given that your dependent variable is called u is a function of x, y, z, x squared y cubed plus z to the 4th. And then you're given that x is a function of p. So p is the only independent variable for the inner function. Z is equal to p sine p. So then the question is, what is du dp? And I'm using d instead of partial because if we chain the 2 functions together, u depends on only one variable, p. So it's an ordinary derivative, not a partial derivative. So the pattern for a chain rule is, okay, u depends on, it's good to have this understanding of how variables interact, x, y, and z. But x, y, and z themselves all depend on p. So ultimately use a function of p. So x, y, and z are your intermediaries. So you differentiate u with respect to each intermediary. So partial of u with respect to x, partial of u with respect to y, partial of u with respect to z. Then each of those intermediaries is differentiated with respect to whatever inner independent variable is right here. So dx dp, dy dp, dz dp. Notice the cancellation pattern. So you have x is here, y is here, z is here, but don't forget at the end, you add them all up. This is a dot product going on here. So that's what the chain rule gives you in this case, where you have one dependent variable, one inner independent variable, and these 3 intermediate variables. So this is a pattern to know for chain rule for similar cases. And so now it's a matter of working out what all these are. So du dx would be, in this case, 2xy cubed. And then dx dp would be what?
1 plus
6p, okay. And then we have du dy. So we go back up here,
X squared, 3y.
okay. And then dy dp, but what do we have to use for that?
rod.
Yeah, so what would it give you?
EP plus PEP.
Yeah, so e to the p plus p e to the p. All right, and then finally du dz, which is just 4z cubed, times, and then I unfortunately got to use product rule again on dz dp. Yeah, so maybe a little bit inhumane for a real test problem, but that's why it's on the practice test. So, okay, so you're going to get p cosine p plus sine p. Okay, so you're almost there, but don't forget, your final answer must be written in terms of your independent variables, in this case p. So now you have to take all these and substitute them into there. Just like for one variable chain rule. You're evaluating the outer derivative of the outer function at the inner function. That's what's going on here. So you have 2p plus 3p squared p e to the p cubed. I won't work out absolutely everything. And remember what I said on the test, don't spend time simplifying. You don't have it. 3 plus 3p squared squared. P e to the p squared So yeah, this answer is a bit long. And finally, plus 4z cubed, so that's 4 p sine p cosine cubes. Okay, and I'll be absolutely sure that this agrees with what's in my notes, because I easily could have written down something wrong along the way, but nope. Okay, and then you're done. So,
So we can leave it like that on the test?
please do, yes.
Okay.
Yeah, like I said, it actually makes it easier for me as well as you. Okay. Yeah, there's no need to apply these exponents and definitely don't multiply anything out. Okay. Any questions about this one? Okay. All right. Okay. So, well, since the solution is there, and by all means, between now and class time on Friday, when you look at the other three problems, I tried to pick the hardest three to talk about here today. So look at solutions. If you're not sure where the solution comes from, you don't see how to get it yourself, by all means, contact me. Shoot me an email, stuff on my office, whatever, up to the minute of the test, so you can be ready. I'll see you on Friday.